This video we're going to be looking at design flows for stormwater drainage systems for roads. When you are designing the drainage system for a road, the first thing you need to know is what design flows do I need to design the pipes and the manholes and the catch pits and things for. There are several ways you can do this. The simplest and oldest is called the rational method, and it's for simple small areas. Um, there's also ARC, that's Auckland Regional Council Technical Publication 108, which is a more accurate calculation, but it's more complicated than the rational method. The rational method is used in other parts of New Zealand, but in Auckland, they require you to use ARC-TP 108. However, in this video, we're just going to be looking at the rational method. So the rational method is Q equals CIA over 360. So the Q is the design peak flow in cubic meters per second. That is the flow you need to design your pipes for. It's based on a design storm of a certain size and the maximum amount of water that your stormwater system is going to see when that rainstorm is occurring. Meters cubed per second is not a very convenient unit, except for very large catchments. So normally we convert that to liters per second, but in the equation, the result will come out in cubic meters per second. C is the runoff coefficient. We'll talk a bit that more later on. It's a dimensionless unit. I is rainfall intensity, which is millimeters per hour, and A is the catchment area in hectares. You need to use the correct units. The 360, which is the denominator on the equation, corrects the different units that you've got there so that what comes out is meters cubed per second. There are different versions of this using different corrections, but this is the one we're going to use for this video. So let's look at each one of these factors in turn. So the Q is the design flow, that's the result you want to know. C is the runoff coefficient. It allows for the efficiency of runoff over a particular area, and basically it is the percentage of rain that falls on the ground. Some of it is going to infiltrate into the ground, and some of it is going to run off the ground. It is the stuff that runs off the ground that is of concern. That's what you need to design your drainage system for. The rain that infiltrates into the ground, that doesn't enter your drainage system, so therefore you don't have to account for it. So all the C value does is tells you what percentage of the rain that's falling on a particular area is actually going to be entering your stormwater system. So it takes into account soil types, because clays, for example, that would have a very low infiltration, so very high C. Sands would have high infiltration, and therefore the C would be lower. Vegetation can prevent surface impermeability, topography. Steeper slopes, the water is flowing faster over the slope, therefore it has less opportunity to soak in. Natural catchment storage and soil moisture. So those all come into account with the C value. Just to give you a better idea of what we're looking at here. So you can see with natural ground cover, maybe it all depends on the soil, of course. 25% would go deep infiltration, another 25% shallow infiltration. So 50% of the rain is actually going to infiltrate into the ground. 40% is going to, if it's vegetated, is going to evaporate. It's going to be taken up by the trees, and they breathe out carbon dioxide and water. So only 10% of the water that falls on the ground there, the rain, is going to affect your stormwater system. If you get to a more impervious surface, like a built-out area, that changes quite a bit. So maybe 5% is going to go into the ground, 15% is going to go into the ground, maybe 30% evapotranspiration because there's less vegetation, and 55% of the rain that falls on the ground is going to go to your stormwater system. And that is what you need to design your stormwater system for. the 55% of the rainfall that falls on the ground. So looking at some of the C values, so you can see a sandy slope which is flat, it's got 0.1. So only 10% of the rain that falls on a flat sandy soil area with vegetation is actually going to run over land. The rest is going to either be go back into the air via evapotranspiration, or it's going to soak into the ground. Whereas an impervious surface like a road has 0.95%. So 95% of the rain that falls on the road is going to end up in the stormwater system. The other 5% is going to evaporate back into the atmosphere. So these C values here are pretty good, and it's a matter of just picking the right C value and plugging it in. Looking at I is the rainfall intensity. And so what we do when we're designing a system is we have to pick a design storm for various AP. We can't design for the worst storm ever, because then we just have an overly sized system. So what we do is we design for a design storm. AEP, annual exceedance probability, is the probability of a rainfall event of a particular size will be exceeded in any 1 year. In the old days, we used to call it a moderate storm, a 1 in 5 year return period. The trouble with that was that people thought if they had a 1 in 5 year storm, there would be another 5 years before they got another one, and that's not true. So now we use the inverse of that, which is the AEP, which is 20%. So in any 1 year, there is a 20% chance that a storm like this will occur, and it's measured as rainfall depth per hour. So looking at the AEP in a little bit more detail, so it's a difference between a heavy rainfall and a light rainfall. Obviously, if we design the stormwater system for this rainfall event, then this one is going to be okay. So what we need to do is we need to decide on what the intensity of the rain is going to be. And the way we normally do it is for the primary stormwater system, we design it for an AEP of 0.1, which is a 1 in 10 year annual return interval. So let's look at, so to determine that data, you go to the NIWA site. So you go to this site here, and we're going to go there in a minute. You use the design storm, AEP 10% for the primary system, 1% for the secondary system. Time of concentration, that is the time that it takes for the rain to move from the furthest point of the catchment to the drainage system. If you use 10 minute time of concentration, that's the most conservative, and that's what we'll use for this video. But there are ways of calculating the time of concentration, which may reduce the design flow if you've got a larger catchment. We also need to adjust for climate change. So the RCP is the representative concentration pathway. So what's happened is a whole lot of scientists got together and looked at a whole lot of future scenarios. So RCP 2.6 is a moderate scenario for climate change, that the rainfall is going to increase moderately over time. We get carbon dioxide levels down. RCP 8.5 is a bad scenario. That's we don't really do all that well with carbon dioxide removal or reducing it, and we end up with a 3 to 4 degree temperature rise over by the year 2100. So the Auckland Council used to suggest using RCP 4.5, but now they're suggesting RCP 8.5. So let's go and have a look at this HERD site. This gives you the situation. So this is what you get. So what you do is just zoom in to whatever place you want to go to. So I just had to pause it there to find the site that I was looking for. So I think the site, so this is around Unitech Way, where I work. And so this is the closest site. So here it is, Mount Albert Gamma. So I click on this, and what it does is it gives me the opportunity, so it tells me the site ID. You can put latitude and longitude in, or you can sort of search by street name, but it's usually easier just to zoom into the map. So now I generate the report, and what it's doing down the bottom there is it's generating the report. And so let's just go to this RCP 8.5. So we've got the 0.1 um, uh, AEP storm. So the design I is 107 millimeters per hour. If we're looking for if we're designing the secondary system, it's 0.01, which is a 1 in 100-year storm, and it's 156. So you can see that um, we're designing for varying levels of storm. So obviously this is going to be a very rare storm, but when it comes along, it's going to drop 156 millimeters of water in an hour. Whereas this one is going to come through it's going to be several of them. It's going to come through every 10 years on average. So it's got a 10% chance of doing. Just look at this 107 so remember we're using the RCP 8.5. So this is the worst case scenario. This is the least case. So just remember that 107. So 104. So you can see that these scenarios, as you go up the scenarios, you're actually getting to more and more severe storms. It's worthwhile sort of playing around with this and looking at the different scenarios. This is for up to 2031 and 2050. The thing to remember about stormwater systems is you're designing them for 50 to 100 years. So that's why we're looking so far into the future. Sometimes you might use this other chart, which shows that well, it's showing the same amount in another 100 years. So back to the slides. So once again, as I pointed out, you need to look at the difference between those scenarios, but this is the one you designed for with the 10% AEP and the 1% AEP for secondary systems. Here is the sheet that we looked at just before, and it shows that 0.1 AEP for the primary systems and the 0.01 for the secondary systems. Let's look at A. So A is the area of the catchment. If you just look at it, if you think about the intensity is the depth of the flow, and the A is the area of the flow. So all you're looking at there is in 1 hour, if you have a rainstorm of the set intensity on this particular area, that's the volume of water that's going to land on that particular area. And then the C corrects it for the amount of water that's actually going to infiltrate into the ground, is actually going to be runoff and is going to enter your stormwater system. So it's quite a simple formula, and it's very easy. It's easily understood. So once again, the catchment area, we measured in hectares. Once again, maybe only more useful for a larger catchment, but that's what we've got. So let's just look at a catchment area here. We were looking at this before, so let's assume that the water's flowing all the way down. So we're just looking at what's flowing into this splay pit here. So there's a berm here, and the flow from the berm is flowing to the curb, and we've got a road, or half the road here, and that is flowing to the curb as well. So the flow to the curb will be quite low here because most of the flow will have gone to this splay pit here, but then it will build as more water is added, and we're interested in how much water is entering that splay pit at that point there. So what we're going to do is we need to put areas in. So area A is 35 square meters, and it's a grass berm. Remember, when we're looking at the C value, we need to know what type of surface it is. And then area B is 37 square meters, and it's a road. And just for interest, I've also added the area for display pit 6-1 as well. So we're going to look at this one and add them together and figure out what the flow for this pipe is going to be. Thing to remember is that the flow catchment upstream of this is being taken by this manhole. It will these two splay pits, and then they'll go into this manhole, and that will eventually feed into manhole 2.2. But for these splay pits, we're only concerned about what's happening in these areas around here. So let's just put it into calculation. So we've got area A The C is 0.17. If you go back the slide a bit, you'll see that 0.17 is for a grass with clay, which is what this is. The I is 107, which we got from that table that I showed you at hertz. The 35 square meters is from there. And see, I've converted it to 0.0035 hectares. So 10,000 square meters equals 1 hectare. And I end up with this number here. And as I pointed out before, cubic meters per second is not the best units to be using for a small area like this. So I'm converting it into liters per second, which gives me 0.2 liters per second. Once again, different C value because it's a road, it's impermeable. So with this rain falling here, 83% is going to soak into the ground and 17% is going to flow there. On the road, 95% is going to flow to the display pit, and only 5% is going to probably evaporate into the air. So once again, we do it for both sides. We add them together. They both contribute to it, so we end up with a Q of 1.2 liters per second. I know those types of splay pits have a capacity of 75, so that splay pit is more than big enough to cope with that. Do it with the other side, and once again we end up with 1.2 liters per second going into a splay pit which has a capacity of 75, so we know that splay pit's okay. We add them both together, we end up with 2.4, and then so now we're looking at the flow that's coming out of this manhole here. So there's a flow coming in from there, which is 1.2, flow from there, which is 1.2, and then whatever you calculated for the flow coming from this catchment here. And then that is what you would use to determine the size of this pipe here. So we're going to look at the design of the pipes in later videos, but in this one, hopefully you now know how to figure out what that design flow is going to be for each of the components that you're designing.